Welcome, everyone. Thanks for being here today. 35 years of impact in math and science education, T-Cubed International Conference. Virtually, we are all here. As we begin the session, I want to welcome you and also say, find that chat panel over there. However you can access it depending on your device. Share with us, please, where you're from, what you teach, information like that. And a reminder that at the close of this session, you'll be getting a brief survey. If you've attended a TI webinar before, you know how important they are in terms of helping us plan and prepare not only the presenters, but the people who plan the program offerings that are available. Resources and recordings will be available to us, all of us attendees. Within a week or so, we'll get emails using the email address for which that we used for registering for the conference. It'll share links and other information. The slides will probably be in PDF form and with some other calculator files as well, and links to resources. From one session to the next, they might have different ways of sharing the resource, but overall, the conference documents will be shared via email. That email will also have information about a certificate of attendance link. I'll answer more questions on that towards the end or in a chat if I need to, and because I don't want to take up any more time from our great presenters. Our presenters for this session are Vicki Carter and Karen Slino. Vicki had recently retired after teaching high school math for 46 years at West Florence High School in Florence, South Carolina. She's a former co-chair of the AP Calculus Development Committee and is currently serving as an AP Calculus consultant. She received the T-Cube Leadership Award in 2015 and has been on the TI-Nspire authoring team that have presented at many state, national, and local conferences. Welcome, Vicki, and thank you for being here. Our other presenter for this session is Karen Slino. She's taught AP Calculus for the past 25 over 32 years in the classroom, and this year is also teaching AP Pre-Calculus. She's currently on the AP Calculus Development Committee and serves as an exam leader at the readings. For the past 8 years, she's led workshops for AP Calculus teachers around the country, and she said she's thrilled to become a T-Cube regional instructor. Congratulations and welcome. In 2022, she was named Regional Teacher of the Year in Michigan, and in 2023, a Presidential Awardee State Finalist. So, welcome, ladies. Thank you so much. If I said something incorrect or if there's more you want to share, I'm turning it over to you now. I'm also going to be monitoring the chat to see if there's anything that I need to do over there. So thank you. Thank you, ladies. Over to you.
All right. Well, good morning, everyone, or good afternoon. I see we have a representation from Singapore, from India, and from Portugal, so that's really exciting. And it's great to be here this afternoon. All right, I am going to go ahead and start sharing my screen. Okay, so when Vicki and I were talking about what we should present about today, we thought, you know, one of the topics that comes up a lot on the AP exam, like almost every year, is particle motion. And that's true for AB and for BC. And we also started thinking, you know, there are a lot of things that students do that sometimes lose them points that are just little things that are so easily remedied, especially if you use technology. So we thought this would be the perfect storm to bring together some AP topics and some technology topics as well. So let's get started. So as you just saw, our agenda for today will be to kind of start with a warm-up of just thinking about graphs of functions and their derivatives and what we can tell from those. We will then kind of move into talking about some common student errors that happen both at the reading and also just misunderstandings with technology. Things that where students are just not using their TI-Nspires appropriately or even to their utmost benefit. And then from there, we'll take a look at question AB2 from this year's AP exam. that is on particle motion. Well, actually, it's not a particle, but we'll get to that. And we'll kind of talk about how the calculator can help students to navigate things like that. So let's jump right in. Okay, for this presentation, we will be relying a lot on one of Vicky's Mix 6 worksheets. So Vicky, do you want to talk about how those work?
Yes, I'll be happy to. I'm actually going to put a link into the chat. I did a blog post on this for TI back about a year ago, and it has a lot of information in it. A mix 6, though, is basically following Bloom's taxonomy. It consists of 6 questions. I really loved it, and I started using them a lot for review in my AP calculus class the last year I taught, and I'm now writing a lot for AP pre-calculus. But it's 6 questions that start fairly easy. So first we have factual recall. What do we want every student to know about the topic? And in this case, we're kind of looking at derivatives with particle motion. The second one is carry out a procedure. I think of this as a procedure that you would expect most students to be able to do without having to have assistance from the teacher or others, classmates or something. Then classify a mathematical object. I really like this part. Some of these are Venn diagrams. Some of them are select all that are true, true, false, different things like that, but sort of this classification idea. The one that's perfect for AP Calculus is prove, show, justify. Then we have extend a concept is the fifth one. I think of this as a little more in depth than carry out a procedure. I love the fact that they're aligned vertically, right on one above the other. And so that kind of makes it a good skill that the two in the center are skill practices. And then the last is my favorite, critique a fallacy. Once you have a little bit of experience with teaching AP Calculus, you know the kinds of mistakes students make. And so I love to think of these. I've got a good friend who takes pictures of mistakes, so he has a good one to put into that category. But basically, you kind of show an incorrect solution and you ask the students to find where the problem is and correct it.
Okay, thanks so much, Vicky. So this QR code will take you to that document, but I think Vicky also put a link in the chat as well so that you can follow along with us. So as she mentioned, the very first box in the Mix 6 is about factual recall. So I'm not sure where all of you are in your AP journey as an educator. So let's just kind of start from the beginning and make sure we're all on the same place. So the question is, we have a particle that's moving along the x-axis with a position given by x of t, which is pretty common. What is the relationship between position and velocity? And then the second question, what is the relationship between position, velocity, and acceleration? So again, it's factual recall. This is what we would hope all of our students would find a really easy question. So let's take a look at what we would hope they would answer to these questions. So the first of all, the x of t. So this is something that students should expect when we're talking about position, that t will be usually our independent variable. Sometimes it's an s of t, sometimes it's x of t, but we're not usually using x as our independent variable. And we'll talk about that a little bit more in a moment. So to answer the first question, velocity is x prime of t, the derivative of it. Acceleration is v prime of t, or x double prime of t, and that's your acceleration. And then just a little bonus factoid there, the absolute value of velocity is speed. So I would like to mention the way that I have written these response answers, and also the way Vicky has set them up in the Mix 6, is something really important when it comes to communication on the AP exam. So most of the time, particle questions are calculator questions as well. So for example, if a student was asked to find, let's say, the velocity at time 3, and all they write is, and let's say they were given a position function. If all they write is v of 3 equals a number, that likely is not going to get the full amount of points because they have not communicated what they're doing. So we know that there are certain skills on the AP exam that students can use their calculator and not show work. And finding a derivative at a point is one of those. However, if all they write is v of 3 equals a number and they were given a position function, they have not communicated what they did with that position function to get to that v of 3. So the way that you see things written on this slide is exactly the way that I'm enforcing things in my classroom too. So when students are finding velocity, they are writing v of t equals x prime of t. And when they're finding acceleration, they're writing a of t equals v prime of t or x double prime of t. So they're communicating what they're doing with the given function in order to answer the question that was posed. Another thing I'd like to mention while we're here, and that's in the note at the bottom of the slide, and that is when the student is asked for a specific velocity, let's say, at a time, many times we see students writing v of t equals that value. And so when they do that, what they're essentially saying is that the velocity is 5 all the time for all values of t, and that's not true. So they really need to communicate that v of 3 is 5, not v of t is 5. And that definitely could cost them a point on the AP exam. So those are just a couple little nuggets to kind of keep in mind that if you're reinforcing that kind of communication consistently, the students will follow through too. Okay, let's do a little warm up here with derivatives and their graphs. So I stole this function from a 2022 exam. This was AB6. And so what you are seeing here are 3 graphs. One of them represents a position function, one of them represents velocity, and one of them represents acceleration. So I would like you to decide which one is which. And so if you could put your answers in the chat, Vicki will keep an eye on that for us, and then we'll have the big reveal.
So just use the letters. So the first letter would represent which one you think is position. The second letter you type would be velocity, and the third one would be acceleration. So like, is it ABC or BAC or CBA? So Karen, we have a couple of responses in the chat.
Okay.
CAB seems to be popular.
Oh, okay. Well, we shall see if that is right. Are we ready for the big reveal?
Yes.
Here we go. So position was indeed C, velocity was A, and acceleration was B. So well done if you answered CAB. That is absolutely right. So that could be a really great warm-up for your students, is to give them 3 functions graphed and say which one is the derivative of which one. And more importantly, how did you know? So it's not just a matter of getting the right answer, but being able to explain what they saw in the graphs that led them to their conclusion. I think another question that we could then ask once that's determined is, so what can we say about the particle's motion at time 3? And so now we can think about, where is that particle located? What is the velocity of that particle and what does that mean? And what is the acceleration of that particle? We could even ask, is this particle speeding up or slowing down at time 3 based on these graphs? So kind of putting these things right together on the slide where students have to analyze and think, that really plays into the communication mathematical practice of the exam, and is something that they will likely have to respond to on a free response question as well. So that's, now we've got our minds in the game. It's time now to move into what kind of things do we have misconceptions about. So we are going to begin with what a graph can tell us. So this is question 3 on the mix 6. So for time greater than 0, a particle is moving along the x-axis with a position given by the sine function that you see there. For which of the following times is the particle moving to the right? And so we have 4 times given, and we would like to know when the particle is moving right. So when students are beginning their study of particle motion, they may think, well, maybe I should just substitute those values into the function. Maybe that will work. But really what that's doing is telling us where the particle is at those times. Not so much about the motion of the particle, but the location. So the next step we have to think about is, well, how would we know if a particle is moving right? And of course, we would know that if the velocity was positive at that time. So how can we determine if the velocity is positive? So one thing that students might do if they're not using technology would say, well, I have to find the derivative, of course. And you know, when you're in a testing situation, your mind's not always working quite as well as it is when you're not. And so an error could happen really easily. Usually it's an arithmetic error that happens really easily. So using technology for a question like this will remove that possibility because the calculator will get the graph right. So let's take a look at how we might solve this on the Nspire. So here we have a graph of what this sine function looks like from time 0 to 10. So that definitely covers all of the times that we're being asked about. And we might be able to look at this and say, okay, well, at time 1, it kind of looks like we have a positive value. But of course, that's a position. That's not a velocity. It doesn't really tell us if we're moving right or not. So what we might want to do is to graph the derivative of this function at the same time. And I'll show you how to do that in just a moment. But what you'll notice is I didn't find the derivative analytically. I made the calculator do it for us. So now we can look at this graph and say, well, at time 1, I'm not sure. I could go to trace and see what that red curve is doing, but I really would want to know for sure if I have a positive or a negative velocity. So the next step would be, let's bring up the table. And when we see the table along with the graph, and this is the table for our velocity function, we can look at time 1 and say, oh, absolutely. Time 1 has a velocity of 0.688. That's a positive value. So at time 1, this particle is moving to the right. And we can do the same for time 2, 4, and 6. So I'm going to bring up my Nspire so we can kind of walk through that process of how you can help students to use their calculator to envision what's happening. Okay, so here we have our graph. And I've got it actually going negative 10 to 10, which is all lovely. And so we would now like to get a picture of what does the derivative look like. So I'm going to add a function, but instead of taking the derivative, I'm going to use my Nspire to actually find the derivative for me. So if I go to that template button right here, you will see in the second row, we have a ddx or dd something option. So I'm going to choose that. We are taking this derivative with respect to x, and we are doing this for the function f1 of x. So now I have a picture of the derivative, and I didn't have to worry about any errors on my part because I made the calculator create the graph for me. So that's a really cool way to kind of make students feel confident in the technology telling them the right thing because they don't have to worry about their own errors potentially. So now let's bring that table in. So I'm going to do a Control T. And now we have the table for F1, which is our position. But now I arrow over and I can see here we have all of those velocity values. So at time 1, we know that we have a positive velocity, we're moving right. At time 2, we have a negative velocity, we are moving left. At time 4, positive velocity, we're moving right. And time 6, negative velocity, we're moving left. So that's one way we could have our students really think about this question and see the visual as well. There's another way, though, we could answer this question, and that's by using a store feature on a calculator page. So I'm going to add a page that is a calculator page, and what we're going to do is enter that velocity function, which was, I believe, I'm a 5. Let me double check for sure.
That's your position.
Yep, and I want 5. Right, that's true. I don't want that one. So what we are going to do, and we're going to call this V of t.
Well, we might want to call it S of t, X of t.
Oh, it's called
or
X of t. Okay.
S of t. Yeah.
Okay.
There you go.
Okay. So the way we're going to store, there's a little colon equal sign right above that template button. And so we're going to insert that. And then we want this to be our velocity function, which I think was F5, correct?
Yeah.
Yeah. Okay. So F5.
No, it was F1. Your position is F1. Oh, yeah.
I
Your
gotcha.
position's
Okay.
F1.
Yep.
Okay. There you go.
I gotcha. Okay. And we probably want to call this T, right, Vicki?
Mm-hmm. Yes.
Okay. Okay. And so what we've done now is told this calculator that whenever we do something with x of t, it's actually going to refer back to our f1. So remember, we wanted derivative values, right? So what we can do is go now to our menu. We go to calculus, and we're finding a derivative at a point. Now we need to be careful. We are using the t variable here, so we need to make sure that we are inserting a t. And for our value, we are looking for this value at 1. So now we just need to insert our x of t that we just defined. And ta-da, there is our 0.688. So this is another way that we can say, oh, the velocity is positive, we are moving to the right. And then it's really easy to just arrow up, do a copy paste, and change the t value to 2. And now we have our negative velocity so that we are moving to the left. So those are 2 ways that we can use the TI-Nspire to help students get their answers, feel confident in their answers, and even to visualize exactly what's happening.
So Karen and I talked when we were preparing this about, why would you show students a different way? I have found through the years, and I use the TI-Nspire in my AP Calculus class for a number of years, pretty much since it was available. Some students prefer one way and some students prefer the other way. And so I sort of let them be the judge of which way am I going to remember? Which one seems more natural to me when I'm taking the AP exam? And the students need to have lots of experiences with using the various methods so they can kind of figure out their I guess it's like their personality of what they like to do on the calculator.
That is so true, so true. Okay, so let's take another look at something that may come up on the AP exam. All right, so this time we have a function. This time we're given the velocity. So it's t minus 1 quantity squared times t minus 3. And there are a couple of questions that could be asked. One of them is, when does the particle's motion stop? And the other is, when does the particle change direction? And if you've taught AP Calculus for a while, you know many times students think this is the same question. So we do the same thing, we get the same answers. But we know as teachers that's not the case. So here's what we would probably do on paper if we were asked one of these questions. We would set our velocity equal to 0, we would solve it, and we would get time 1 and time 3. And for some students, that would be the end of the road. They'd say, okay, this is what's happening. The particle is stopping and changing direction at time 1 and time 3. But there's a little bit more we have to consider. Stopping means the velocity is 0. So I agree that question 1 has been answered. But changing direction, that's something else. That means that velocity is changing sign at these times. And we really don't know that. We just know this particle has stopped. So again, using the technology to visualize what's happening makes this a much more rich question for us. So here we have a picture of this function. And once the students see this, they can very easily see, okay, at time 3, this function is changing from negative to positive. So we do have a change in direction at time 3. But at time 1, we do not have a change in direction. This function is going from negative to negative. So the particle's just taking a break. He's tired. He's been running. So he's just taking a break, but he's going to keep going in the same direction he was traveling. And we don't see that with the analytical work, but we see it when we look at the graph. I'd also like to mention here, the same kind of thinking is true for finding inflection points. So every year I have students who, they know we set the second derivative equal to 0 and we solve it. And that's good, but if there isn't a change in concavity, then there isn't an inflection point. So they also need to think this way when the context is finding inflection points as well. Okay, on to our next question. This is from the Mix 6. This is number 4. So we are in the prove, show, and justify, which is always fun. So in this situation, for t greater than or equal to 0, a particle is moving along the y-axis with this velocity you see. So let's find all the times where the particle changes direction. Justify your answer. So I'm going to give you about 30 seconds or so to enter that into your calculator, and then I will do the same, and we'll see what we think.
Karen, you're going to need to do document new problem because your X got stored while ago as a function.
Oh, okay, so just make a new document.
Just press document.
Okay.
Go down to insert, new problem, number 1.
Got it. Okay.
Okay, now do your Go to your
There we
graph
go.
screen.
Okay.
There you go.
There we go. Thanks for the help.
And that is also a part of this calculator that's probably something that students need to realize, and they need to see how to add a new problem because it kind of cleans the slate but keeps you in the same document. But all their F1s and F2s are cleared so they can start back over. And anytime you store something as an X or a T or a Y or something that you might be using, you have to be a little bit careful.
Okay, so I'm being a student right now, and here I am entering my function, and we're good to go, right? That looks
Yep.
exactly like what I just saw on my problem, and what just happened? So we wanted to make sure we showed you this because your students will do the same, and many times they don't pay attention to a variable, they just type what they see on their paper. And so since we've defined this function notation as f1 of x, the calculator is looking for x's to be in their function, and if not, it's going to create a slider for them, which in some cases is what we want to have happen, but not in this case. So I wanted to make sure we all saw what happens if you use the incorrect variable. But I'm going to go back because I do have it entered correctly here somewhere. Oops. Nope, next one. There we go. Okay. So here we have the correct function. So now we can take a look at this and say, all right, this is velocity. So we are looking for not only when this function equals 0, but also when it's changing direction. And I can see very clearly there are 2 times that this is happening. So
Karen, I think it because you're back in problem 1. I've messed you up a little bit, and I apologize. When we stored something as X, it's grabbing your other X, so that's not the correct. It's actually doing a composition.
Oh my gosh, oh my gosh. Okay, so how do we fix this, Vicki?
We go back you're gonna have to type it in again. Just go back to your 2.1 page.
Okay.
So we're learning a lot about our
We
calculator
are,
today.
right? Okay, so here
Yes. And these are the same kind of things that students are going to do. If you go up and just change those X's, those T's to X's, you don't have to change your function, just make them X's. There you go. And this is a lot of the things that I'll do it wrong in class too. It's funny how I know better and I'll still do it incorrectly. And we've got to get your exponent. I think, what is it, 4/5?
right?
Yeah.
Okay.
So be aware that with the TI-Nspire, it's easy to do some things like this and just make students aware of what's going on.
Okay, I'm not seeing my graph happening though, so.
Oh, that's funny.
I know. It is. You know what? I'm just going to go back to my slide. Actually, yeah, let's do that. We'll just
Okay, let's just go back to the slide. Yeah. Oh, you typed
we have it here. So there we go.
You typed 4/3, not 4/5.
Oh, okay. Let's go back and fix that. My goodness.
Thanks.
When it rains, it pours. Let's get this
does.
right.
There you go. 4/5.
Yeah. Oh, that's not right either.
That's still not right.
Back to the slide. That's
yeah,
okay.
back to the slides. There we go.
So anyway, so this is what we would want to see.
It's a lot of pressure doing this.
It is, right. And just like when you're teaching, these things happen. So at this point, what we would want to do, of course, is take a look at those 2 values where we are crossing the x-axis and then find those. And that also is something I wanted to mention. So I'll go back to one of my other graphs to show when students are buying new calculators, many times they will be getting results that are not correct to 3 decimal places. So I'm going to go back to the graph, even though it was the wrong one, and we're going to take a look at how do we fix that. Okay, so even though this is the incorrect graph, let's pretend it's the right one. So we will go to menu and to analyze graph, and we are looking for a 0, of course. So we're going to put our 2 lines around the 0, and here it is. But on the AP exam, this would not get full credit because it's only 2 decimal places of accuracy. So that's an issue. So when students come to you with this issue, it's very easy to fix. We just go to menu, we go down to settings, and you'll notice this is where it says how many digits are we displaying. So we want to make this as many as possible. I just say go down to 9, and then you will see much more accuracy. And once they do it once at the beginning of the year, they are good for the rest of the year then.
All right, Karen, go back and put it on what it was originally because there's another way they can see more digits.
Okay.
And I just wanted everybody to be aware of this because students might not want to go to that trouble of having to go change their settings. A lot of students will, I always encourage mine, let's get your calculator set up before we walk into the AP exam.
For sure.
And so make sure you're in radian mode, all those kinds of things. Hover over the -2.9 and press your plus key. You might have, if you're on the stop, yeah, press again. There you go. And we can see more digits.
There we go.
And one of the things that I am going to caution both the teachers and you caution your students about is sometimes if it's only displaying 3 digits past the decimal, it might be rounding and it might round incorrectly. So I always encourage my students to look at 4 or 5 digits to the left of the decimal. I mean, to the right of the decimal. So making sure that they don't put a rounded answer that is not going to be accepted on the AP exam.
Good point. Okay. So back to our misconceptions. Whoops. Let's take a look at the next one. We're on to number 6 now. So this is such a common error with students on the AP exam when they're asked about, is the particle speeding up or slowing down? So in this question, for t greater than or equal to 0, we have this particle moving along the x-axis, and the velocity is given as 2t cubed minus 3t minus 1. So when is the particle speeding up? So Riley has an answer and Julia has a different answer. So who is correct? So the misconception here many times is that the students are looking at this function and thinking, well, if it's a positive velocity, we must be speeding up, right? So what do we need to have them think about? So again, if they were to create a graph, they would definitely see this velocity function, and they might be able to look at that and say, I see some positive velocity, so let's just find those x-intercepts and call it a day. But we know there's a little bit more to the story. If we were to graph that derivative of velocity, then we can really talk about, well, what's happening? And it's really confusing for students at first when they realize that a negative velocity and a negative acceleration actually means you're speeding up. So I try to describe it with walking into the wind versus walking with the wind, right? It doesn't matter what direction you're going, but if you're walking a direction and the wind's going that way too, you're going to be speeding up. And if you're walking into the wind, you're going to be slowing down. So in these values where you're seeing a negative velocity and a negative acceleration, those are actually times when this particle is going to be speeding up. And so that's a great way to kind of reinforce that. So it's an important point to say that positive velocity is not increasing velocity. That's something we cannot say too many times. Positive velocity is not increasing velocity.
Or sometimes they'll just find acceleration and go with whatever the
Yes,
acceleration is. If acceleration is positive, they just think, I don't need to bother with velocity. I'm just going to say speeding up.
exactly. Okay. So we are now ready to talk about 2023's AB2, and it is a particle motion, but as I said, it's not a particle, it's Stephen. And Stephen is swimming back and forth on a straight path in a pool for 90 seconds. And we see his velocity is given by this combination of an exponential and sine function. So
Karen,
definitely,
pause just a second. So in
yep,
case you're not real familiar with the format of the AP exam for your response questions, questions 1 and 2 are calculator active. So I know that if I'm working with AB2, it's calculator active. I also see that obnoxious velocity function and sure hope I have my calculator.
absolutely. And so message 1 to the students is that function needs to be put into your calculator immediately because you know you'll be doing various things with it. And so Vicki is going to kind of walk us through some of the parts of this question and the things that she would recommend we do. But let's first of all look at what kind of things students are being asked to do. So in part A, we would like to find all the times between time 0 and 90 where Stephen is changing direction. So we've talked about this already. We know that does not just mean when is the velocity 0, but also when is there a sign change in velocity. And they are asked to give a reason for their answer. And then part B, we are looking for Stephen's acceleration at time 60. So I want to make a note here. This is one of those 4 things that a student can just give the answer because they're using their calculator to get the value. But they do need to communicate what did they do with that velocity function to get to that acceleration value at time 60. So it even reminds them, show the setup for your calculations indicate units of measure. And then we're also asked, is Stephen speeding up or slowing down at this time? And we know we need to think about velocity and acceleration at this time. Give a reason for your answer. Part C is asking for the distance between Stephen's position at time 20 seconds and time 80 seconds. Again, show the setup for the calculations. And part D, find the total distance that Stephen is swimming from time 0 to 90 seconds and show the setup for your calculations. So let's go over to our calculator. And we're going to open another file here. Okay, Vicki. So what would we do for part A? We're looking for the times where the Stephen is changing direction.
Okay, so the first thing I would do is store the function on the calculator. So Karen already has it typed in here. V of t, you do need to use the colon equals. This is where students will sometimes forget that it's actually a computer kind of thing that students that have studied some computer languages may know, but they can't just put equals. It won't work. If they've got to see a done after they press enter, otherwise they've messed up somewhere. So if you're going to store this as v of t, then you're using t as your independent variable. And I think this is how, for me, I highly recommended this for my students because it's now in the notation that they see on the paper. And I always told them, I know you're under a time pressure. You've got approximately 15 minutes to do this free response question, but make absolutely certain every decimal is typed in correctly, because if you type this wrong, even if you're using the f1 of x to type it in, because that's how some students do it, they put it in the graph first, they've got to make sure that they have typed in exactly what they see on the paper. So we've got that typed in, and now we have done. And our first question is to find all times on t in the interval from 0 to 90 at which Stephen changes direction. So I would go to the graphing application, which we have already put here. Notice that even though we've already done it, we have f1 of x equals v of x. Okay, so when I had my prompt for f1 up there, I needed to make sure I typed v of x. If I had typed v of t, which students will do, and I'm going to admit I sometimes carelessly do it too. If you recall, Karen got that slider for t that popped up on the window. So I said, if you ever get that notice about a slider, you typed a t, not an x. You've got the wrong independent variable. So that's a really good hint for students to think about when they're doing the graphing. So we have the graph here. We did a menu. Just go through the steps to show how I got the 56. So menu, analyze graph, and we were finding a 0. And again, you'll have a lower bound, so you'd want to go to the left, and then an upper bound, and you'd want to go to the right. And there's our 0. We got it a second time. This is the only time in that interval from 0 to 90. And I purposely set up my screen to show that window, even though it's not a square window. I wanted to see a window that matched the context of the problem. So I can clearly see that that is the only time that Stephen changed direction. Karen, let's show them real quick how we can set this window up by going to menu.
Okay.
And go to Windows, Zoom. And sometimes it's like, well, where is it? It's because it's at the very top of the page. You're looking at all this zoom, 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 zoom. It's at the very top of the page. It's already highlighted. It's Windows settings. And so since I knew that Stephen was swimming in the pool for 90, was it 90 seconds or something, then I know I want my X-min to be 0, my X-max to be 90. Some teachers like to put a little cushion on each side, so they might do -1 to 91 or something like that. But in this particular problem, 0 to 90 works well. And then I just kind of judged what I was seeing when I did 0 to 90 to get my Y min and Y max. I also like to change scales to something that makes sense. Do not, yes, you can use Zoom Fit. This just came up in the comment. Do not use Zoom Fit until you have set your X min and X max. So I would go into this window, set my X min, X max, and then I could go back and do Zoom Fit and it would fit my Ys. Please, I almost want to slap the students' hands. Of course, I'm not. I'm figuratively speaking, but if they did Zoom Fit without setting their domain, it can make it's just can create havoc with graphs that they are working with. So be very careful in the use of Zoom Fit with the TI-Nspire.
And I also will mention, we were just doing some graphing yesterday, and the students will go to, if they can't see the graph immediately, zoom out is immediately where they go, and that doesn't always give a good window either. So it's a learning curve for them to realize window settings is the place to go, at least initially, and then you can tweak from there.
Yeah, and that's really important in a contextually based situation. And we think of all particle motion as contextual light because we're introducing a particle. In this case, there was heavy context with Stephen swimming in a pool.
Right.
All right, so we've got our 56 as our solution. On the AP exam, they had to talk about the fact that there was a sign change at, they had to consider a sign change at t equals 56, and then they, of course, had to have their answer that he changed directions when the velocity changed signs, and this occurs at t equals 56 seconds.
And this is a good time to remind your students also, saying things like it changes signs or the function changes signs is not going to do it, because we don't know what function you're talking about or what it is for that matter. So sometimes they hate being specific, but they learn that that's where the bar is. So
yes.
The velocity changes sign. That's why we're changing direction. Okay.
All right. So now we want to find Stephen's acceleration at t equals 60 seconds. I don't know why it's at the bottom of the page, but there it is.
Okay.
So this is using the derivative at a point that Karen demonstrated earlier. So we found the derivative. Karen, let's just go through the steps again. Just repeat it so they can see what we're doing.
Okay.
So we're going to menu, calculus, and it's numerical derivative at a point. We want to put in our independent variable as t because we defined our position as our velocity as t, and the point is, I forgot, 60. Okay, so we stored the velocity function and we're finding acceleration. Now, here's the beauty of storing that function initially. A student should never have to type a function that is in the stem of the problem but one time. So now they reference their v of t that they stored it, and they press enter, and they have their acceleration.
Nice.
On the AP exam, they need to clearly note that they are finding the derivative of v at t equals 60. We used to have to go through a big process of telling students not to use calculator syntax, but now the beauty of the TI-Nspire is the calculator syntax is the syntax that we can actually use. So they could write down what they have on the left and equals what they have on the right, and then include, I think units needed to be in this one.
Yes.
So it would be meters per second, and they're good to go with the first part of that question.
Right. And also just a reminder, having that t equals 60 there is absolutely critical. So just saying the derivative of velocity is negative 0.036 is not going to do it. So they need to have that 60 there. Okay.
Okay, now we want to know if Stephen is speeding up or slowing down. We cannot, and this is one of the misconceptions, we cannot look at that acceleration and say, oh, it's negative, he must be slowing down, because we also need to consider the velocity. Again, here's the beauty of storing that function. Karen can just type v of 60, and now here side by side, or top and bottom, sorry, we have clearly both the velocity and the acceleration are negative, same sign, the particle is speeding up. They need to explain that both the velocity at 60 and the acceleration at 60 are negative or have the same sign. I don't see anything in the chat about questions, so we must be doing okay. So now we want to know, we want to find the distance between Stephen's position at time t equals 20 seconds and his position at time t equals 80 seconds. Okay, this is not asking for total distance traveled. This is asking how he was here at 20 seconds, he was here at 60 seconds. How far apart are those positions at those two times? So it's very important that students know that this is integrating, finding the definite integral from 20 to 80 of v of t dt, which turns out to be 23.384. Karen, here's what I'd like for you to do.
Sure.
I don't know where your cursor is right now. Scroll up and highlight that 20. Go up one more. Just highlight that answer, not the integral. Go to the right, highlight the answer.
Okay. There.
Yep.
That one? Okay.
Yep. Press enter. So sometimes I tell students, it's displaying those three decimal places there. Maybe you need to look and make sure whether it did. The students have to be real careful about whether they're writing a rounded or truncated answer. And sometimes the rounded and truncated answer is the same. And sometimes, of course, the rounding causes the two representations to be one digit difference. They've got to make sure that what they're writing down is correct for either method. So in this case, 23.383 would be correct, or 23.384, which is that rounded answer the calculator had given, would also earn them full credit for this. Press enter one more time just so it won't tag that into something else. All right, good. All right, part C, find the distance between Stephen's position. No, that's the one we just did. Sorry about that. Now we want to find the total distance that Stephen swims over the time interval from 0 to 90. So very clearly, total distance. They've got to see that word. That's very important. Yes, Peter added that we need to make sure, again, that on the AP exam, they're labeling what they're writing down. So like Karen said, you can't say V of t equals a number. You need to say V of whatever, 60 equals the number. So make sure that they are practicing good mathematical notation. I am very strict in the classroom, grading their assignments or their quizzes, tests, anything that I'm assessing them on about notation. I'll just add this as a little aside. I actually had a whole bunch of pre-ink stamps that said things like, watch your notation, different things like that. Take the derivative. The famous one, of course, was chain rule. Chain rule, chain rule. I had a student one time came back after class and said, I'm going to have to buy you some more ink. I said, what are you talking about? And he said, well, we took the chain rule quiz today and I forgot to do the chain rule, so you're going to run out of ink. I said, okay.
Oh my gosh.
But I tell you what, those self-inking stamp messages on their papers really sent the message to them. They were like, I don't want to get a stamp today. Anyway, just as an aside, it's something that you can do in the classroom that kind of makes teaching fun and learning fun, and we all get to laugh about it together.
And probably you could have one that says DX or DT on it too.
Oh yeah, I had
That
one
would
of
be
those
used
too.
a lot.
And this is probably not a good. I had one that it was just bad algebra with an exclamation mark.
I like it.
All right, so now we want that total distance. So it's very important that the students use the absolute value of velocity. So Karen, scroll down to the bottom of the screen. Let's retype this for everybody because we haven't actually typed in a definite integral yet.
Okay.
All right, so let's go to menu, calculus. And now we have a numerical integral. Okay, we get these little boxes to fill in. So we want to go from 0 to 90. And then some students don't have a clue where to find the absolute value sign or symbol. There are actually two ways to do it. So let's go through the first one, which is using the template, Karen. So get our template there. And absolute values on the top row, far right. And we just, remember, we've stored V of t. So all we need to do now is type V of t, and then with respect to t. I love this about this calculator. because they cannot forget their differential. They have to type it in. And the fact that they type it in repeatedly, I think helps them to remember that they need to write it when they're
True.
doing an assessment. So there we get it. Let's do it a different way because this is actually what I typically use. So menu, calculus, numeric integral, okay, 0, 90. And in the box, type A, B, S, just using your keyboard, and parenthesis, V of T, DT, press enter. Oh, look what it does. So I love that, especially when I'm working perhaps at a keyboard rather than on my calculator. That is one of the things that I really enjoy doing. So you can remind students, that may be another thing that they have a preference as to whether they want to go to the template or whether they want to actually type in ABS. All right, we've answered the questions. So now I want to show you something else that's pretty powerful about the calculator. Karen, I don't remember what slide it's on. Is it on the third slide, maybe? Ah, yes. Okay, so I decided to take this a little further and give you a demonstration here of Stephen's motion as he swims in the pool. So I set my window from 0 to 55. The pool was only, it was like 50 feet or something like that, 50 meters. I can't remember what it was. All right, so I'm actually graphing in parametric mode right now. I know that parametric motion, actually, there's a session coming up right behind this one on BC parametric motion, is a BC topic, but it's really fun to demonstrate this to students in the classroom. But you would need to set it up in parametric mode. So I defined x1 of t to be the definite integral, and I decided, hey, I want Stephen to start at the edge of the pool. So I could start him somewhere else, but this was just my way of demonstrating this. So 0 to t, and now I have to use a different independent variable. Sometimes we refer to it as a dummy variable, which my students thought was hilarious that we were going to call a variable dumb, but whatever. But it's not the same thing. It's just a dummy variable. So we do have to type in something like v of x dx. And then I decided, let's put Stephen in lane 1 of the pool, okay? If I want to put him in lane 2, I could have typed y1 of t equals 2, but I selected 1. So I get this graph. What I'd really like to see is Stephen actually swimming across this pool. So if you will go to menu, and we want to go to trace, and let's just double check what our trace step is because I don't remember what I set it up for. Let's put in, I think it's 3 works pretty well.
Okay.
Okay. And I could be wrong, but we'll see. Now go back to menu again and trace. And this time we want path plot. And we have a parametric, so we have to go to parametric. And you have a little play button. So click on the play button. And
there
here
he
goes Stephen.
goes.
There's Stephen. This could be a particle. Now watch the numbers down at the bottom.
He's swimming away.
He's swimming. When was he? We don't have time. But anyway, so he almost gets to the other edge of the pool. And he kicks and turns around and
Stephen.
Look at Stephen go back the other way.
Love it.
And when should that have happened? It should have happened at t equals 56. And the time was clicking across there. I was looking at the x and y coordinates. So you can demo this, and kids love this. So one of the things that teachers kind of liked about the TI-84 was that they could see the parametric equation being graphed. But that's just because it was slow. It was having to plot these little points along the way. It really wasn't the motion, but it looked like it. And we kind of lost that with the TI-Nspire at first because it was just like had so much power. It's like, poof, here's the graph. But now with this path plot, you can see the motion of the particle, or in this case, Stephen, and it is really an eye-opening experience for the students. So that's kind of what we wanted to show. I don't think we have much going on in the chat. Are there some questions that some of you have? Yes, you can do car races, so you could set up two.
Mhm.
We could get Karen and Steven competing in the pool, one in lane 1 and one in lane 2,
Right.
and we can see what's happening. Okay, they want to see how to graph parametrically, so let's see if we can do
Okay.
this. So just open a new page, put in a graphing screen. Okay, so go to menu and go to graph entry edit. You've got to select parametric.
Mhm.
Okay, now here's the nice thing again about having stored that. So we want to enter the integral. So you need a definite integral.
Okay. Are we wanting this here?
Yeah, that's fine. The last
Um,
one on the second row.
oh, there we go. Got it.
There we go.
Okay.
Okay, 0 to 90. Wasn't that it? Yeah, I think it's 90.
Yep.
Okay, and then we have to put in the dummy variable, so we're gonna have to put v of x dx. And then y2 is just what, silly, I'm calling it a lane. We'll put 1. Okay, now something real important, Karen. We've got to go down to that last line where it says 0 to 6.28.
Mm-hmm.
We've got to change that to 90. It's got to reflect the, okay, press enter. Oh, why isn't it there?
Why isn't it there? Good question.
I don't know. Did I type something in incorrectly?
That's
Go
okay.
back to 1.3.
Oh, we need a T. That's why.
Oh, what did we put? Oh,
Let's put a
yes, we
90.
needed T. I was thinking about the 90.
There
There
we
we go.
go.
Okay, then we have to adjust the window to the 0 to 90. There you go. And then you just go through the steps that we did, which was menu, trace.
Trace. Mhm.
And the only reason I said that trace step to change it, because if you put it, leave it like default, I think it's like 1, and it is, Stephen is going very slow. If we made it 5, he'd go faster. So make
Let's
it
go
5, so
faster.
he can
Yes.
go a little
Let's do
faster.
it. Okay.
All right, then you have to go back to menu, trace, and path plot, parametric, and play. Well,
So
we somehow messed up. We're at 0.1. Stephen is going at, he's a turtle.
he's a very slow swimmer.
He's very slow. So that you can see that it's really important
Yeah.
that you get these settings correct. And honestly, if you're going to demonstrate this in the classroom, get it all set up ahead of time.
Yeah.
All right, Karen, we're pretty much right. 3 minutes to go. I
We
think Ruth's
are,
got to
yes.
do some closing stuff for
All
us.
right.
It's all yours, Ruth.
Thank you. Thank you, ladies. The chat is still open for people who want to ask questions or share comments. So go ahead and do that. Let's see. So I think we're to the point now of, as we're wrapping up, finding out more from the chat. And here we go. The lucky winner is Phyllis Oquan. Phyllis Oquan, thank you so much for, well, congratulations, Phyllis. Woohoo!
Yay,
All right.
Phyllis. Thank you, everyone.
Awesome. Thank you.
All right. As we've mentioned, not only in this session, but in other sessions you may have heard, we attendees will be receiving an email next week with information how to locate the resources. They'll be on the conference website, however that's going to be organized for us. And so we will be able to find the resources for the session. It will also include links to the recordings and linked so that you can create a certificate of attendance. That's all I've got to say. Congratulations and thanks everybody for your time. Thank you, ladies, so much for your presentation and for sharing your wealth of experience and your resources with us.